Okay, so this is only for recording. It has no amplification. It's just uncomfortable. Okay. So feel free to stop me to ask any questions, comments. Interaction is more important than me speaking something which you do not understand. So stop me anytime. So the title of my talk is Black Holes and Gravitational Waves. And the key thing that I will explain in this talk is this graph. Um, the older among you might have seen this graph in newspapers a few years back, but if you have not seen, you will understand what this is. Okay, so so on February 11th, 2016, so about 7 years ago, the first detection of gravitational waves was announced. And this was not only the first detection of gravitational waves, but also first direct observation of black hole binaries. So in that sense, the first direct observation of black hole binaries was also announced. And this was also the first test of strong field, strong gravity, high velocity, and nonlinear general relativity. So let me just say a few things about this. So all of you know that there are a lot of satellite experiments that NASA does, or like even ISRO does, where we send probes in the sky and we look for various general relativistic effect, like GPS, for example. GPS is, all of you have GPS on your phone, and this uses general relativity in an important way. So in some sense, all the many tests of general relativity we do on a regular basis. But those tests are all in the weak field, weak gravity. Like here, I mean, although gravity is very strong here, but but it's very weak compared to the other forces, electromagnetic forces and things like those. So when we are talking about this event, we are talking about very strong gravitational field, very massive stars colliding with each other, stars or black holes, things like those colliding with each other, and also moving very fast. So they are moving close to thousands of kilometers per second velocity. And nonlinear part you may or may not appreciate, but this perhaps will become clear as we go further. Okay, so this announcement marks a new era of physics, in the sense that now one can do a lot of things. Like if we can observe gravitational waves, then we can actually look into the sky through gravitational waves and try to ask more detailed questions about astrophysics, about properties of neutron stars, properties of black holes, and things like those. So this is the context in which these announcements uh, were path breaking, and they set a new era in physics. So in this talk, I will present the context of this discovery. And the discovery combines many subjects. General relativity, crowning achievement. General relativity is a crowning achievement of classical physics. There is a lot of math, lot of computing, and very lot of engineering. Mm. So I will only focus on the physics part because that's what I know. This math, computing, and engineering stuff I do not know. So I will only focus on the physics part. Okay, so what is LIGO? So the instrument that did these discoveries is called LIGO. So LIGO is an instrument. The full form is laser interferometer gravitational observatory. Okay, and what it saw the merger of two black holes, one of mass 29 solar masses and the other of mass 36 solar masses. Okay, so these black holes were really heavy. Um, both of them more than 25 solar masses. Okay, and they were very far away. They were at a distance of 400 megaparsec, which is about 1 billion light years. So I hope all of you understand this. What do I mean by 29 solar masses? Uh, 29 times the, yeah. Question? Somebody said, sir. Uh, Yeah. Okay. And do people know parsec? Parsec 3.26 light years. Definition of parsec, you know? Hmm? Very good. Yeah. So when you look at a star and by the motion of the Earth in 6 months, you will see a parallax of 1 second. That is the distance of the star is 1 parsec. And this was, you see, very, very high number, 400 megaparsecs. So that's very, very far away. Okay. And the announcement was made by LIGO director. And in his characteristic style, he said, ladies and gentlemen, we have detected gravitational waves. We did it. Okay, so to appreciate what all this is, what all this is about, we need to look at um, a little bit of what is called general relativity and few things about black holes. Okay, so these are very big subjects. Like I work on these subjects, so all my life I have been doing this thing. Um, so general relativity is a theory of gravity developed by Albert Einstein in 1915. In Newton's theory of gravity, the forces, like one talks about forces acting between different bodies. Um, like in Newton's first law, second law, third law, like there are like forces acting on bodies. But in Einstein's theory, something different happens. In Einstein's theory, in some sense, there are no forces, but forces are manifested as curvature of space-time, curvature of space-time around the object. So I will show a picture how this comes about. So here is an example. So if two particles are moving on straight lines in a plane, then you will say that there are no forces acting on them. So they are just moving Newton's first law. No forces acting, so they move in straight line and they continue to move in straight line. But suppose you put these particles on the sphere, then although you started them parallel, like you will started them at some distance without going towards each other, but as they go towards the pole, you see they will come together. Okay, so see, although in some sense there are no forces acting on this system, but because of the geometry of the space-time, the particles are coming together. So this is how Einstein's theory like sort of incorporates forces. Yeah. Just gravity. In Einstein's theory is only gravity. Yeah. The other forces are put in by other means. Yeah. So here is another example. So suppose this was a too simple a geometry, but suppose a geometry is like this, which is actually more realistic in the case of black holes. So you have some faraway region, and then you have a well kind of shape, and then you fall into the well. So these two people, let's say these two people, like these two people on these two lines, suppose they are falling into the this well, then just because of the geometry of the well, they will come closer and they will feel some force among each other. Yeah. Sorry, I did not understand. Yeah, we are two people, two objects. Yeah. Yeah. Yes. Yeah. No, no, no. Um, e- Even if see, you cannot stop the moon in time. So this diagram is too simplistic. Okay, let me first explain this diagram, then I will answer your question. Okay, so you see, so another thing I wanted to say about this diagram is that you see these two lines here, they are parallel, but if you draw like parallel lines here, they are coming together. And if you draw a triangle here, so the triangle has sum of angles to be 180 degrees. But if you draw a triangle, just take this triangle and transport it here, then it will have different properties. And same is true with the circle. Okay, so now to answer your question, so these diagrams are only in space, but when the moon is moving or when the gravitational force is acting between the Earth and the moon, it's also motion in time. So when you say you stop the moon continues to move in time. So you get a path. Uh, yeah, yeah. Okay, so how two freely falling observers come close to each other, all that is explained by this curvature of the space-time. Um, and not only the things come close together, but also the time is behaving differently. Um, in strong gravitational field, the clock behaves differently compared to the clock in a no gravitational field. So all of you might have seen, some of you might have seen this movie Interstellars. Interstellar talks a lot about this clocks and times and so on. Yeah. Yeah, 2D surface. Yeah. Space is actually even the 3D surface is not correct. It's a four-dimensional object where time direction is one direction and three other directions are there. No, no, no. This is not what Einstein did. This is just my naive picture to explain. Einstein wrote mathematical equations to explain all that. So Einstein made a theory in four dimensions. One dimension is time, and the other are three space dimension. And he wrote equations for how the particles move, how objects come close together, and things like those. Yeah. But these pictures are like at a junior level. These pictures do capture the main essence. Uh, yeah. Okay, is this other questions, comments? Okay, so in Einstein's theory, there are some exotic objects, and these objects are called black holes, and these are the hallmark of general relativity. So black holes are region of space-time where nothing can escape. So there is a special surface, and this surface acts as a one-way membrane. Things can fall in, but they cannot come out. Um, and because of this one-way nature, you can think of them as these are places where there is an extreme distortion of space-time, like extreme distortion from the notions that we are used to. I mean, I can go up this stair and come back down, but in a black hole, you cannot do that. You can only go one way. You cannot come back. So, so in some sense, these are extreme distortions of space-time. These objects exist in nature. I will give you reasons why they exist. Because by definition, you cannot see them because only things fall in, nothing can come out. So if nothing is coming out, then by definition, you cannot see them. So observing a black hole is a mystery in itself. What do you mean by observing? Yeah. So you see the way I started my talk, if you go back, um, where was I? Yeah, so I said that these are general relativity is a crowning achievement of classical physics. So Hawking effect is quantum physics. So in this talk, I will not discuss any quantum aspects. I will only focus on the classical aspects. So in the classical aspects, black holes um, are just objects which are one-way membrane, and they don't have temperature uh, and things like those. Yeah, and yeah, yeah. Yeah. So, uh, okay, let me just say one more thing. So, before answering that question, so these black holes play an important role in the evolution of stars and galaxies in the sense that since there are a lot of forces near the black hole, if a star is orbiting, then it feels a lot of like tidal forces, and it can be ripped apart and things like those. So it does play an important role in the evolution of galaxies. Yeah, yeah, Malaka. Okay, so to answer the question that you were asking, so this one-way membrane is called the horizon, and this surface is completely smooth. So one can go from outside to inside, nothing special will happen. These are for point particles, absolutely nothing special will happen. You can just go from outside to inside. Um, but the question is, how far can you go inside? How long in time you can go inside? So it turns out that in general relativity, you cannot go very long in time. So as soon as you cross the black hole, after some finite amount of time, you will hit something called a singularity. And at the singularity, everything stops. Sort of the space time, everything ends there. So the way it shows up in the equations is distances are, like, roughly speaking, functions of 2m over r, where m is the mass of the black hole. And when r is, so as you can see, if when r is greater than 2m, nothing special is happening. Like it's just positive numbers. But when r becomes less than 2m, the space and time sort of change roles. And uh, and if you go from r equal to 2m to r equal to 0, you do this in uh, finite amount of time. So r is the distance from the r minus 2m is the distance from the black hole. You can think of it like this. It's the, oh, since you are a coordinate distance uh, from the center, if you wish. Yeah. Okay, so did I answer your question? So I mean, the key point is that there is 1 over r term, and as r goes to 0, there is some infinity. No, it appears. This is actually, if you know the metric tensor, this is the component of the metric tensor. So ds square is minus 1 minus 2m over r dt squared plus lambda. So actually, this is a term in the metric tensor. Yeah. No, because he was asking about the quantum. He said Hawking radiation, but Hawking radiation has some temperature, but that is a quantum effect. But I'm discussing classical physics. In classical physics, there are no temperature. I mean, there is no concept of temperature for a black hole in classical physics. Yeah. Okay. Other questions, comments? Okay. Very good. So how do black holes form? So most of the black holes in nature that we know, they form by collapse of massive stars. So if you take a very heavy star, 15 solar masses or so, and you collapse it, like just squeeze it very hard, then it will become a black hole. And this results in a black holes which are sometimes called solar mass black holes. They have masses of in the range 3 to 100 solar masses. Okay, so mathematics wise, these solar mass black holes and other heavier black holes, there is no difference. There are other kinds of black holes which are called supermassive black holes. Mathematically, they are not any different. It's just this m is a real number. So it can be a small, large, that doesn't matter. But physics wise, there is a big difference. Supermassive black holes, they are billions of solar masses, and they exist at the center of the galaxies. It is not fully understood how these black holes form, because what we understand is how these small black holes form, but like how these very big black holes form physics wise is not fully clear. The current accepted theory is that they start out small and then grow slowly by eating more stars and swallowing gases and other objects in the nearby environment. And that's how they grow, and they become so big that they have billions and billions, millions to billions of masses. Okay, so the basic mechanism is collapse of the star. You might have heard that, like a big star, after it runs out of the hydrogen helium fuel, it will start to collapse and it will become a black hole. Okay, so black holes do exist, and one can study the existence of black hole by looking at the motion of stars near the Milky Way, for example, near the center of the Milky Way. So I will show you a video of the star, and this video is taken over last 10 years. Not last 10 years, about 10 years. 1992 it starts and ends at 2002. And this is motion of the stars around the center of our galaxy. And this is one of the strongest evidence that black holes exist. And Nobel Prize was given for this discovery few years back. Okay, so this is how so you see, we don't see any special object at the cross, but if we just look at these stars over a long period of time, this is how they move. And this is a very strong evidence that So there is a special star in this called S2 star, and the orbit of perhaps this one, the one whose orbit you see completely. So this star especially has been analyzed in a lot of detail, and one of the key evidence that Milky Way center has a black hole. Okay. So this is the same picture, just uh, the curves are drawn, and you can see the motion of the stars is such that it points that there is a very heavy object at the center, and that is supposed to be a black hole. Okay, so this is all I wanted to say about black holes. So questions, comments. Black holes is a very big topic. Like it has hundreds and thousands of properties. So whatever questions you might have, I may try to address them. No? Yeah, like so when r becomes less than 2m, the minus sign of this also changes, and this is the sense in which the space and time change. So this was like the so the way to think of it, the time direction comes with a minus sign, but when r becomes less than 2m, then because of the sign change, this becomes a space direction. And physics wise, what happens is like um, I will try to draw the light cones. Um, so this is r direction. So the way this happens is that there is a 45-degree line, which is everywhere the same. And then at infinity, the 45-degree line is actually 45 degree. And then as you go closer, it becomes less and less. And when you come at r equal to 2m, it becomes like this. So the light cones behave like this. So when you are far away from the black hole, you move like this. There is no problem. As you come closer to the black hole, you are tilted towards the black hole. But when you come at the horizon, then you don't have any choice, but you just have to move like this. So there is no way you can try to get out of the, yeah. Yeah, so and this comes about also with the change in the minus sign of the metric. So it so happens that once you cross, you don't have enough time left. You just hit the singularity in finite time. Yeah, time in the sense of your clock. Like once you fall, the clock has to stop at some point. In the proper time, in the frame of reference of your clock. Yeah. Okay, so let me say a few things about gravitational waves and the relation between gravitational waves and black holes. Yes, please. The time is defined by saying that um, the, the definition of time, time is defined just by um, far away from the black hole is just the the time that your clock measures is the time. Yeah. So like the I don't know how to explain it in words, actually, sorry. I only know how to write it in equations. Uh, Time stops in the sense that yeah, okay, that part I can answer. But first, but you asked a difficult questions before. What is the definition of time? So by the definition of time, what I meant was as r goes to infinity, you see this term just becomes zero. So the time interval, the proper time interval is just minus dt squared. So the clock time and the time that we call t is the same. Uh, what I meant by time stops is that once you cross r equal to 2m, you ask how much time I have before I hit the singularity, before I hit r equal to 0. And that time is finite. So once you hit the singularity, then sort of space and time ends. You have nothing left. And yeah, yes, please. No, no, no. So ds square can be negative or positive. Um, oh, no, oh, okay. So this is interval. Yeah, I understand what you mean. So this has a name. This is called an interval, which people use the notation ds squared. But this ds square can interval can be positive or negative, and you bracket outside or inside. Yeah. No, this is ds squared. Yeah. Yeah, but so you are right. This is the issue of the time in Einstein's theory of relativity. The intervals in time directions are negative number, and intervals in space directions are positive numbers. In your notation, it will be imaginary numbers, if that's what you mean. Imaginary number in time direction, real numbers in space direction. Yeah. Okay, thanks. Okay, so now gravitational waves. So when two black holes come close to each other, they experience forces because of curvature of the space-time around each other, and then this happens. Okay, so they come together and they emit a lot of radiation. So this radiation that comes out is called the gravitational radiation. Okay, so many of you might have heard that accelerating charged particles radiate. So the phenomena is mathematically the phenomena is exactly the same. Accelerating gravitational point particles radiate. So black holes are models for that, and black holes radiate. Uh, no, not in Newtonian gravity. Newtonian gravity doesn't have those. In charged particles in Maxwell theory radiate. Uh, yeah, yeah, you can think of it that way. Yeah, yeah. No, no, no. Maxwell's theory. I mean, you need all these corrections, what are called displacement currents, and whatever all these corrections are called. I forget the name. Ampere's law and those correct. Hmm? Ampere Maxwell law. So you need all those corrections. Once you write the full Maxwell's equations with all the corrections included, charged particles radiate. Accelerating charged particles radiate. Yeah, they are invariant under relativistic. Uh, yeah, symmetries and so on. Exactly the same theory applies. I mean literally exactly like the same equations, the same wave operators and everything applies. They are I mean not equal, very similar. Yeah, yeah. Yeah. No, that is a separate physics input. So in electrodynamics, there are two types of charges: positive charges, negative charges. In general relativity, there is only one type of charge: positive masses. There are no negative masses. But positive charges radiate, negative charges radiate. In general relativity, only positive charges are radiating. Yeah. Okay. So what are gravitational waves or gravity waves? Um, so these are fluctuations produced by moving masses. And moving masses have to have some details, like not like like in electrostatics that you study in one of the first equation, Coulomb's law, F equal to Q over 1 over 4 pi epsilon naught r squared. That formula has no radiation. It's just Coulomb's law. But the particle has to accelerate, particle has to move in some funny way, then only. So similarly, in general relativity, the particle has to do something. And what it has to do is it has to have time-dependent quadrupole moment. Okay, if so, for example, my body has quadrupole moments. When I'm shaking my hands, some gravitational radiation is coming out. So time-dependent quadrupole moment is responsible for the motion of these gravitational waves. And these waves travel at the speed of light, exactly like in electrodynamics, and they have same equations. And they carry energy and momentum. Like you can actually heat your food, like as in a microwave, you can heat your food using these gravitational waves. They actually carry energy and momentum, and they are not easy to detect because these are fluctuations in the space time. So I mean, when I'm moving my hands, some radiation is coming out, but that radiation is so weak that we cannot detect. And once detected, they have enormous science potential because of the astrophysics one can do using them. Yeah, yeah. The okay. Well, let me write some equations. Okay, so this is the equation for wave equation in electrodynamics. I don't know if you have seen this. So this is the wave operator. This is the Maxwell potential. In general relativity, the equation is this. So exactly the same operator, but slightly different object. So um, so as long as the equations are concerned, they are the same. But then because of this difference between one versus two indices, there are some details which are different. And specifically the dipole moment in first case and quadrupole moment in the second case. So dipole moment here, quadrupole moment here. Yeah. 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 Exactly. Yeah, exactly. So let me write the formula. So dipole moment in electrodynamics is Q times sum over. Okay, but um, you don't need positive or negative. In order to have a invariant meaning, like in order for D to be unambiguous, you need the condition that the total charge should be zero. This is the problem. No? If you change the origin, that is, if you change the origin by C, then D is ambiguous. That's the problem. But in general relativity, that doesn't happen. Um, that requires a writing more equations. uh, I don't want to get into that, but yeah. But in general relativity, that doesn't happen. Yeah, it's not ambiguous. You can, yeah. Total mass can be anything. Yeah, exactly. Yeah, energy and momentum. Yeah, exactly. The formulas are very similar. So electromagnetic waves carry um, momentum, which is proportional to E cross B, the Poynting vector. And they carry energy, which is epsilon 0 E squared over 2 plus 1 over 2 mu 0 B squared. So these are the electromagnetic uh, energy density and momentum density. The formulas for gravitational waves are very similar. You have to do something else because the indices and so on, but the theory, the formulas, everything is very similar. Yeah. Okay. So sources. So as we discussed, moving matter produces gravitational waves, exactly like moving charge particles produce electromagnetic waves. And one of the simplest example is this. For this also, there was a Nobel Prize given. So here there is a neutron star um, around another neutron star or another black hole, whatever. And they rotate. And as they rotate, some radiation comes out, and that radiation reflects into changes in the properties of this neutron stars. In the sense that if the neutron star is spinning, then the rate of the spin goes down because there is an energy loss from the system. And one can plot this as a function of time over 20 years, and one finds that it matches exactly with the prediction of general relativity. And this is called Hulse-Taylor binary pulsar. Okay, and for discovering this pulsar and doing all this analysis, there was a Nobel Prize given to these authors. Okay, so what are gravitational waves? So when gravitational wave comes, this is what happens. So they are like fluctuations in your space-time. So if you take a ring of particle and ask how the gravitational waves are affecting that ring of particle, this is how they affect. So in this picture, gravitational waves are traveling in this direction, and you have a ring of particle. This is how they are getting deformed. Here is another example. This is a picture from Pune, Ayuka, and gravitational wave comes, and the photo of Einstein gets stretched, deformed. So there are two type of polarizations that one can talk about. So one is this cross polarization, where the Einstein photo is, and there is a circular polarization where it sort of get deformed in the circular way. Okay, so these are the two independent polarization of gravitational waves. Yeah, so electromagnetism has linearly polarized light. Uh, Linearly polarized light, you can think of it linear combination of right circularly, left circularly. So yeah, so there are two polarization in electrodynamics. In gravitational wave, also two polarization. Yeah. Okay, so let me now say a few things about LIGO and LIGO India. So when the announcement was made of LIGO results, LIGO India was also sort of formally signed. And this is our PM, the director of LIGO project, NSF director. So what is LIGO? So LIGO is a long interferometer arms. So it's a 4 kilometer arms in each direction. And what is happening is that laser is bouncing between these arms. And there is an extraordinary effort to avoid forces on the mirrors, which are test masses, to reach the sensitivity that you want to reach in order to do the observations. And what it does is that it looks at the fractional changes in the length of the arm, and it does it to this much accuracy. Delta L over L is 10 to the power minus 21. Yeah. 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 They have a, yeah. 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 No, no, no. The attenuation is, yeah. The attenuation is just the effect that the waves are traveling in all directions. So you see, this light, yeah, it's just this attenuation. Yeah. 1 over r square. Yeah. Okay, so these are the two detectors. So one is at Hanford on the northwest side of the US, and one is in Livingston, which is the southeast side of the US. And each of these detectors have 4 kilometers arms each, and they do interferometers like this. So these are the two pictures of the detectors. And this is how this works. So instead of saying, you can just look at it. So one of these L arms, so this is the laser. Okay, so the laser bounces between these mirrors. Okay, and perfect overlap, so destructive interference. So you don't see any light in this part. Okay, now the gravitational wave comes. So gravitational wave comes, so you see this length is changing or this length is changing, and then there is a interference. Okay, so this is the signal we are trying to see. Okay, so as the wave is coming, the lengths are changing, and because of these changes in length, we are seeing the interference pattern at the detector. Yeah, this I will show in the next slide. Yeah. Okay, is this clear? This is how the detection is done. So there is a global network of detectors. These are the LIGOs, which are in the US, and there are European detectors and Japanese detectors. So in Europe, there is Virgo and Geo. Geo is in Germany, Virgo is in Italy, Kagra is in Japan, and LIGO India will come up in some time. Uh, the location was secret for many years, but now it has been announced. So this is near Hindol district in Maharashtra. Um, there is a famous Gurudwara there. Um, I forget the name. Uh, I forget the Hajur Sahib, perhaps Hajur Sahib. Yeah, there is a Gurudwara there. It's near that in that area. Hindol. Okay. So yeah, to answer your question about the frequency and so the way it happens is that when the gravitational wave signal comes, it comes in a specific form. Like as we saw in the beginning, let me go back and yeah, so it comes actually in this form. So, so this is the signal that we will see at Earth. So it will have uh, like oscillations of this type. So what we do is that we draw the time series of how the interference pattern is changing, and that time series gives us the data. Yeah. Okay. So where are we? LIGO. So LIGO India. So LIGO India is a wonderful project. Now it has been fully approved. All the money is with the people who will make this instrument. So it's so India will provide the infrastructure to house this detector. The detector will be given by the LIGO project. Um, and as far as I understand, the detector has not yet been shipped because the infrastructure facility is not yet ready, but it will come in some years or some time. Uh, the main advantage of LIGO India is that right now we cannot locate the object from where the gravitational waves are coming in the sky. So right now, this is all we can say, that from the Livingston and the Hanford detector, we can only say that the signal are coming from these patches in the sky. But once we have LIGO India, we will be able to say more precisely where exactly the signal is coming from in the sky. So we will be able to say more details about the location of the sources in the sky. We will be able to say more about the polarization of the waves in the sky. And of course, because we will have three detectors of the same technology, we will have greater uh, time to observe the 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 signal. Hmm? The other no, they are also very advanced, but they are just different. So just by using these three, we will be able to locate. Yeah, combine the data. Yeah, combine the data from all. Yeah. Okay, so the discovery, let me say a few things about the discovery of gravitational waves. So this is what I said. It was announced on 11th February, and the paper came out on 12th February. 2016. So this is the title. So many papers came out. This is just one of them. So the title of the paper was Observation of Gravitational Waves from a Binary Black Hole Merger. And many authors, LIGO and Virgo collaboration. So what they said is that there is a 29 solar mass black hole and 36 solar mass black hole, which merge and they produce a 62 solar mass black hole. If you add these numbers, then you see it does not add to 60. It does not add to 62. There is some mass left, and all that mass is radiated in gravitational waves. So this must, they carry a huge amount of energy. But because of this 1 over r square effect, we only see a very tiny part of it. And this is what the instrument saw. So the Hanford instrument saw a time series data. You were asking about the time series. So this is the kind of data that Hanford instrument saw. And this is the data that Livingston instrument saw. And there was a very small time difference between the two because uh, Hanford and Livingston are separated geographically. So it took some time for the gravitational waves to travel from one to the other. But once you shift this and plot on top of each other, then you see that the signals are very well correlated. So these are the experimental signals. These are the theoretical models. So if you take the theoretical models and subtract the signals, then you get only noise. And similarly here, only noise. So this is uh, the discovery that was reported on 11th of February 2016. Okay, now let me say a few things about future, because 2016 was already 7 years ago. So the future is LISA. This is a laser interferometer space antenna. So the idea is that we send these satellites in the sky, and this interference pattern will be done by the satellites. So this is a space-based gravitational wave observatory building on the success of LISA Pathfinder. So this was a mission that was done a couple of years ago. This is a very successful mission. This mission is led by, and the whole program is led by European Space Agency in collaboration with NASA and other organizations. So this is actually an actual photo of LISA Pathfinder satellite. The picture is like this. So there will be 3 satellites, 1, 2, 3, and there will be lasers running between them. And these lasers will do various types of interferometry. And if a gravitational wave signal comes, then the lengths between the arms of these satellites will change, and they will measure the the changes in changes in yeah. So these are really extreme technology. So there are 3 satellites. Each arm on Earth is 4 kilometers. Even 4 kilometers was very difficult to build, but now it is 2.5 million kilometers. And these will be following the Earth, in the sense that as Earth goes around the orbit of the sun, these satellites will following the Earth, and they will be just 15 million kilometers behind the Earth, and they will do these observations and experiments. Yes. How do you make sure that drift out of focus? So actually, so many people had this doubt, and this is the reason there was this LISA Pathfinder mission. So LISA Pathfinder mission was just to check the technology, whether the technology that scientists are talking about that works or not. So they tested a number of things, that one can maintain the proper distance between satellites, and not only proper distance. I mean, there are a lot of other details, like the mirrors from which the reflection happens. Those mirrors have to be like very precise, and they move as real free bodies inside the satellite, and the satellite adjusts itself around the mirrors. So it's a very fancy technology that that this mission does. You can read about LISA more if you're interested. So LISA, it traces the origin. It will trace the origin, growth, and mergers of supermassive black holes. One thing I forgot to say. Actually, this focuses on the low frequency gravitational waves, because the lengths are so long, so one can talk about longer wavelength modes. So the LISA science will trace the origin of supermassive black holes through ages, cosmic ages. It will help us understand the expansion of the universe. There are a lot of puzzles in cosmology about the Hubble's constant and things like those. And it will explore the fundamental nature of gravity and black holes in different regime, low frequency regime. And it will also help us understand the gravitational waves which were produced at early stages of the universe. Okay, so this is all I wanted to say. Now I'm happy to summarize and take questions. So we have come a long way in our understanding of gravitational waves and black holes. There are many unanswered questions just in classical physics without getting into quantum aspects. Gravitational waves are a new window to the universe, and LIGO India will come up in a couple of years, and it will help in locating gravitational wave sources in the sky. LISA project will come up. So LISA project will help us understand other mysteries of the universe. It will focus on gravitational waves in the low frequency regime. So the future of gravitational wave research is very bright. This is all I wanted to say. So thank you. Okay, so yeah, I'm happy to take all sorts of questions. Yeah. No, no, no. Is the the interferometer is very fancy, but as the gravitational wave comes, what will happen is that there will be a difference in the arm lengths of this and this, for example. So then it will observe the interference pattern. Yeah. It's exactly like LIGO, but at a bigger scale. Yeah. And they will have some more fancy technology about interferometry and so on, all that they will have, but the basic idea is that. Yeah. Yes, please. If you look at, sorry. Oh, the signal is larger in the other one. Okay. Okay. Yeah, it can be. I don't know the details of this. Um, I doubt because it's the same signal just translated in time. So the difference can be just noise. Difference. Then there is also this noise. So it depends on how this noise is being transported on that. Yeah, there is also this issue. Yeah, indeed. So there is also polarization of the gravitational wave, and also at what angle they are reaching the detector. So not only at what angle, the orientation of the detector is. So you see, it's an L-shaped detector. If the gravitational wave is coming like this, then it makes a difference whether the L is like this or versus like this. So there is also a difference of that. Yeah, yeah. No, 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 no. No, that depends on the wavelength. So the wavelength, see, when we discussed motion of point particle in electromagnetic field, we only care about electric field as a function of time. So the force is Q times E of t. Okay, in electrodynamics, the force on a charged particle is just Q times E of t. So that aspect is not there. I mean, the oh, the X dependence somehow don't matter in this. That requires a bit more explanation, but it's only the time series that matters. Yeah, 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 yeah. So yeah, it's a combined. So there is a detailed analysis one can do of how electromagnetic waves behave in the presence of gravitational waves, and that account. Yeah, I understand. Yeah, my waist will will change. So yeah, so indeed. So this presentation was a bit too simplistic. One can look at a detailed analysis of electromagnetic waves coupled to gravitational waves and ask how the interference pattern will happen. Yeah. Just 1 second. Yeah. So stay quiet. Yeah. 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 Yeah, yeah. Bending of light will change with time. Gravitational bending of light was detected. Yeah, Eddington, yes. No, yeah, 1912 or something like that. You're right, 1920. Yeah. No, no, no. The effects are very different. Um, so you see, the bending of light is the phenomena that um, so the yeah. So here we are on Earth. Here there is a star, and uh, during a solar eclipse, the light from the star is visible at Earth. But if you naively look at it, then the star is just behind the sun. So how is that possible? This is the bending of light phenomena. The way Eddington discovered this. um like if this object is, so you see, so first of all, this was only done with the sun. It was not done with other objects which are radiating. But even if there is object radiating, the fluctuations in this line are very small. Yeah. Okay. Yeah. Yeah. Oh my God. Okay. Yeah. Ah, so these are called, so okay, non-metric theories I don't know, but there are a lot of alternative theories of gravity. um so far no departure from Einstein's theory has been observed. So, I mean, one can never rule out whether other theories are there or not there, but whatever we have done so far, everything seems to match perfectly. Like people have, in particular in this case, people have done a lot of analysis about the data of this noise, and there is nothing in the noise, it's just pure noise. So far, everything matches perfectly with the predictions of general relativity. Like orbits of the stars, for example, that I was showing earlier, these orbits, yeah, I mean, these orbits were done using the geometry of rotating black holes and matches perfectly. So, no, because general relativity is the theory of nature. That's what you, yeah. So there are other alternative theories, but alternative theories are not, or we are not at a precision where one can test those things in a scientific way. Yeah. Yeah. Yes. Yeah. 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 There are three. It's a single setup. What he's saying is that there is single setup. Yeah, I don't think it will help in the so no. So it will verification. What do you mean by verify? The the high frequency component of that you will be measured at LIGO. So you can always cross correlate LISA observations with LIGO observation, but that will only happen at the high frequency range. Low frequency range, you have to trust LISA. Yeah. No, the wavelengths are so low that it's difficult to come. If you think physics wise, it's difficult to come up with models which can give rise to that kind of fluctuations. Yeah. Yeah, wavelengths are so high, low frequencies. Yeah, it's difficult to come up with model which can lead to that kind of fluctuations. Yeah. Yes. Yeah. Um, it's not completely clear. Um, so let me give a slightly technical answer, which is perhaps the only good answer that I can give. Relic gravitational waves. So when the universe started, it was not exactly homogeneous and isotropic, because it just a big bang happened, something happened and it started. Then over time it became homogeneous and isotropic. So this difference between initial and becoming homogeneous and isotropic, these are called gravitational perturbations. So these perturbations are the same as gravitational waves. So when they moved in time, when we see them now, they are the relic gravitational waves. So you can think of these are like initial differences between homogeneous and isotropic universe versus the homogeneous and isotropic universe that we see now. These are the relics. Yeah. Primordial. I mean, many names, relic gravitational waves, primordial gravitational waves, whatever. Yeah. Yeah. Imaginary number question that's come to me. Yeah, indeed it is true, but somehow.
They also brought a
Oh, a pot. Yeah, my wife will be very happy. Thank you.
It's an indoor plant.
yes.
Uh, Now you can just head for lunch. Does everyone have lunch coupon? Does anyone have lunch coupon? You guys have the lunch box.
No, I don't. Yeah. No, I mean just I was that. No, I think only when only as MSc student, we had a small chapter on statistics. That's the MD. Yeah, okay, this, yeah.
Do you have the lunch open?
How will you contact me? Yeah, you can email me. I will try to answer as much as I can. Yeah, what is your name? You are in Chennai? Based in Chennai?
No, I live in Karnataka. Karnataka.
Your name is Kanna.
My name is Kanad. So what's your name?
My full name, Amitabh Virmani.
Is there a age happen to this?
I will try to answer as much as I can, but if I cannot answer, I will give you some reference or Wikipedia article or something.
Thank you so much. I really like that singularity thing.
Who doesn't have the coupons? You do, like who lunch coupons?